So let me give you first a brief overview of what we're doing here. In the first few sections in statistics in this unit, we've been kind of going over what are called descriptive statistics, where we talk about if I have a data set, how do I describe what's going on, right? How do I look at a data set and understand it, right? Consume the data that's there. What we want to do at some point is be able to say, okay, if I have a population, I can take a sample from that population and that'll tell me about the population, right? So we want to be able to look at, maybe a poll of voters to figure out, which way the vote's going, or take a sample of people and ask them a question and figure out how everybody feels, right? So we want to use information from the sample to tell us about the population. Okay, so that's what we're going to start to really do in this section. And the first thing that we need to do is sort of be aware of what type of data that we're working with. The way that we work with data depends on what type of data it is, right? And in particular, at the very beginning of this unit, we split data into our numeric and non-numeric, right? So the qualitative and quantitative, okay? And in a bunch of these sections in 3.4 through 3.7, we looked at almost exclusively numeric data, right? We were looking at mean and standard deviation and z-scores and percentiles, and all of that was for numeric data, okay? And in section 3.8, we were talking about normal distributions, okay? What we're going to do in this section is we're going to come back to a non-numeric variable, right? Qualitative variable. And what we want to do is look at, if I think of my non-numeric variable as being something like a yes or no question, or are you going to vote for this candidate or that one, or something like that, do you like the color blue, then we can summarize the data with the percentage of people that say yes. So not only is our data going to be non-numeric, but we're going to simplify it even further and focus just on like a yes-no question type of situation, right, where we have two responses. Because that's the simplest, and when we introduce a new idea, we want to start with the simpler cases. And in statistics, we can expand from there, but we want to start with something that we can really get a hold of. So what we're going to be doing is we're going to look at proportion P in the population, okay, of people that said yes. All right, so you can think of this as the percentage of people that respond yes. Okay. All right. Now, what we want to make sure that we distinguish in the beginning here is the difference between the percentage of people in the population and the percentage of people in the sample. Okay. So both of these are going to be the percentage of people that say yes, but it's a percentage of different groups. The P that we're using is the percentage in the whole population. So for example, if I want to know how students feel about online learning, and I say, do you think an online class is better than an in-person? Okay, and I could think of all Harper students as being my population, and I could think of just this class as being a sample. So if I ask this class what percentage of people think online learning is better, okay, then the percentage of people that say yes would be the P hat. The percentage of all the Harper students that say yes, that would be the P. And those two wouldn't be the same, okay? But what we're going to do is we're going to use our sample as an estimate for the population proportion. And we're going to talk about different ways that we can estimate it. Okay. All right. So let's go ahead and look at some of these details here. First of all, we want to talk about exactly what our variable is. Okay. And we might have more than one type of variable that we're talking about. Okay. So when we ask a question, when we collect a piece of information from that question, that's a variable. If I look at quantitative data, right, remember this is the numeric. Okay. then my random variable x is going to be some measurement of a randomly selected individual. So we might ask people, you know, how long does it take you to do your homework? Okay. So, for example, if we ask, how long do you spend doing homework? Okay, then that is the random variable. Okay, x would just be how many minutes you spend doing homework. Okay. And then we could also have another random variable, x bar, that is the mean of some randomly selected individuals. So another way to think about the idea of taking a sample, when I go and take a sample, when I select some people at random, that's where the randomness is. And so then the average amount of time they spend doing homework would be a random variable, because if I take a different sample, I'll get a different average. Okay, so x bar is average or mean. Okay, and we can think of this as being a random variable because every different sample will give us a different x bar. Okay, so I sort of have two different random variables from the same question. When I ask how long do you spend doing homework, I get a variable that has a value for each individual, right? And that's the random variable x. And I have another variable that's assigned to each sample I take. So when we take a sample, all of the individuals get their own variable, but then the sample as a whole gets a variable. And I can treat those both as being their own separate random variables. Okay. And the reason that this is a useful idea, the reason that we look at two different random variables, is because my original variable, it might be nice and bell-shaped, or it might be skewed, or it might be uniform, or it might just have some crazy look to it. But as long as I take a big enough sample size, the random variable for x bar will always be a normal distribution. Okay. And that way, even if I don't know what to expect, I know that my random variable for x bar is going to be normally distributed, and that gives me an extra tool. It gives me extra power to be able to compute stuff. Okay. All right. We're going to be looking primarily at qualitative data. Okay, so this is the non-numeric. Okay. And what we need is we need numbers that we can work with. So even when we take non-numeric data, we need to be able to have numbers to work with, because in math, that's kind of our thing. So what we can do, if I ask a question like, do you like blue? Okay, then that's my variable for each individual. But what I can do is I can get a random variable by counting up how many people said yes to that. Okay, so my random variable x would be the number of people that answered yes. Okay, so I can take this non-numeric question and this non-numeric data, and I can sort of get a new numeric variable out of it. Okay, so random variables are always numeric because we need to do computations with them. And then I get this other random variable p hat, and that's just the percentage of people that said yes. Okay. So we're going to focus on this qualitative data. So you don't need to worry about the random variables x and x bar for now. But what we want to do is make sure that we understand that we have two different random variables, right? We could look at x or p hat, and they're both going to be numbers, okay? X is going to be a whole number, okay? So if I ask 10 people, do you like the color blue? I can have anywhere between 0 and 10 yeses, okay? So so if we ask 10 people, we will get between 0 and 10 yes responses. Okay, so there's 11 possibilities. If I ask 10 people, I get 11 possibilities, right? All right. The p hat is the percentage. Okay. Now they give us a formula here, right? P hat is x over n, because if I ask 10 people and 8 people said yes, 8 divided by 10 is how I turn that into a percentage, right? You just divide by how many people you have. Okay. And that's always going to give me a number between 0 and 1, right? So the p hat is a number between 0 and 1, and we can also write it as a percentage. But remember, this percent symbol is just, fraction over 100. So it's really the same number, it's just written a different way. Okay, so the x has to be a whole number. The p hat does not. Okay, the p hat, right, if I ask 7 people, okay, and 3 of them said yes, not only do I not get a whole number, but I get a crazy repeating decimal. Okay, all right. So the p hat is not only going to give me, real numbers, not whole numbers, but if I think of taking big samples, I can get all sorts of different values between 0 and 1, right? There's all sorts of different possible percentages that you can get, okay, when you take a different sample. So as long as my sample size is big enough, I can think of this not only as being a numeric variable, but it turns out it's also going to follow a normal distribution. Okay. So this is going to give us some idea of what to expect, and that allows us to compute some stuff, even if we don't know anything about the answer to our question, right? So that's kind of like the key thing that makes statistics work, right? So this idea that p hat has a normal distribution, and then back here that x bar will always follow this normal distribution, okay? That's called the central limit theorem, and it's kind of like the most important thing in statistics. Okay, let's look at some examples. Students wanted to study some characteristics of peanut M&Ms. So they sampled 1,000 peanut M&Ms and recorded the weight of each M&M. They also recorded from each M&M whether or not the candy was green in color. Okay. Note that more than one measurement can be recorded from an individual in a sample, right? I can look at an M&M and I can look at more than one piece of information. So we're going to break the data types into quantitative and qualitative data. Right? So what we want to do is look at what it is we're talking about, and we want to identify what are the pieces of information that we're working with. Okay. So for the quantitative data, let's start by labeling what is our individual. Right? Our individual is going to be one randomly chosen peanut M&M. our random variable x, okay, remember quantitative is the numeric side, and when I look at the things that I'm writing down, the weight of an M&M is going to be a number that I write down, okay? So that's going to be the weight of a peanut M&M. Okay. My random variable x bar, to draw a bar over it. My random variable x bar is going to be the mean or average weight of, so I sampled 1,000 M&Ms, so it's going to be the average of the 1,000 peanut M&Ms. Okay. On the qualitative side, just remember this is going to be the non-numeric. So on the qualitative side, I want to do the same thing. I want to identify my individual and all the different types of variables that I have. Okay, so my individual here is the same thing. It is a randomly chosen peanut M&M. Okay, the variable, right, the piece of information that I'm writing down that is non-numeric is whether or not it's green in color. Okay, so then my random variable x for my qualitative data side is going to be the number of peanut M&Ms out of the 1,000 that are green. Okay. N in this case is the number of individuals in our sample, right? And our individuals are M&Ms. So I can actually write that down. That's going to be 1,000. So the N is just 1,000 here. Okay. And then the P hat, draw a little hat over this guy. The P hat is going to be that sample proportion. Okay. Or the proportion of the 1,000 M&Ms that are green. Okay. All right, and then remember as a formula, P hat is just x over n. So if I have my random variable x, the number that are green, I just divide that by, in this case, 1,000 to get the percentage or proportion that are green. Okay, let's look at an example. So let's suppose that I ripped open a bag and I count up 1,000 peanut M&Ms, and I count 156 that are green and the 844 that are not green. Excuse me. Okay, so in this case, the number of green M&Ms is 156. Okay, so my x, my random variable x, is 156. And we already said that n is 1,000. Okay, so p hat is x over n, 156 over 1,000, or 0.156. If I were to write that as a percentage, I would say 15.6%. Okay, so for this sample of M&Ms that we have, 15.6% of the M&Ms in our sample are green. Okay, what we can do is we can use that as an estimate for the parameter p. That's the percentage of all peanut M&Ms that are green, not just in our bag, but all of them in the whole world. Right? We could say, all right, 15.6% of all M&Ms are green. Right? And we know that this is really just an estimate. We know that the actual parameter p is probably different, but we don't know what it is. Okay, so in this example, we obtained the sample proportion. And what we want to note is that if this is a good representation of our population, then our estimate should be really close to the percentage of all M&Ms that are green. But we don't expect that these are going to be exactly equal. Okay. And the other thing that we want to note is if we take another sample, right? If we take another bag of M&Ms and we count up how many green M&Ms there are, we would expect that it would be close to 15.6%, but it's probably not going to be exactly that number, right? We're going to get a different number of green M&Ms, so we're going to get a different percentage. Okay, so this value of p hat can vary from one sample to another, but it shouldn't vary by very much. Okay, you might get a rare bag where maybe you get no green M&Ms, or it might be super rare, but maybe like, you know, a 1 in a billion shot, you could get a bag that has like almost all green M&Ms. Okay, but most of the bags of M&Ms are probably going to be very similar, right? Because, you know, the manufacturer makes so many of each, they mix them all up real well and then put them into bags. So, you know, when they get mixed up, then they should all have a, you know, a pretty similar percentage of green ones. Okay. All right. See, I think I want to save this next example. This next example is a really good lead-in to what I wanted to save as the second half. So we're going to save that one for tomorrow. Okay, so I think we're going to call that good for today.